Hey everyone, and welcome to the 29th Annual Goldschmidt Conference. I'm incredibly excited and honored to welcome you to this meeting in the fantastic city of Barcelona. And of course, this meeting would not have come about without the tireless efforts of my co-chair, Derek Vance, our science committee, our local organizing committee, our wonderful team of student volunteers, and of course our sponsors, including our platinum sponsor, Thermo Finnegan. Particularly more than ever, we're taking the sustainability and diversity and inclusivity of something like Goldschmidt really seriously. You might have noticed, for example, that you don't have plastic badge holders anymore, and that you're also being encouraged to try and avoid using disposable coffee cups and water bottles, and the snacks from now on the poster sessions will be vegetarian. We also want Goldschmidt to be a place where everybody feels comfortable and safe, and as part of that, a number of us have received training to be kind of points of contact. A lot of people have asked me what these badges are for. These Amigo badges indicate that if there's anything that you're worried about or you want to talk about, you can contact one of us. And so, really, that's pretty much all to say from me. I hope you have a wonderful week. And I'm now going to hand over to the president of the EAG, Siggy Gislason, and he's now going to present the EAG Awards. So thank you very much.
Thank you very much, Helen. I'm Siggy Gislason I'm the president of the European Association of Geochemistry. Now, the recognition of scientific excellence at all stages of a career is the core of our society's mission. Therefore, it is an honor to present you with the 2019 EAG Awards. Just before starting, I wish to express my sincere thanks to all who submitted nominations. Devoting time to recognition of the achievements of colleagues is very generous. I also want to thank the members of the award committees for their outstanding work selecting this year's medalists. Please note that the nomination for next year's AGU Awards are now open, and I strongly encourage you to submit your nomination before November 15th. We need your help to make sure our pool of nomination reflects the diversity of our community. You can find more information on the EAG website. Now, our first award is the Frederick Houdemans Award, recognizing exceptional contribution made to geochemistry by the young generation. I'm honored to present this award to Stéphane Lalonde from the CNRS and the European Institute of Marine Studies in France. Stéphane's research is focused on the evolution of the Precambrian surface environment of the biosphere. Stéphane is qualified by his peers as one of the leading biochemists of his generation, who has made major advances in how the community approaches the problem of early oxygen production on Earth and how we will understand the origin of oxygen photosynthesis going forwards. Stéphane's research is innovative, multidisciplinary, and is already having a significant impact on the way we view microbe, metal, mineral interactions through time. You will be able to hear Stéphane's metal lecture tomorrow at 8:30 in room 111. Stéphane, in recognition of your exceptional achievement, I am honored to present you with the 2019 Houdemans Medal. Is Stéphane here? We are missing a medalist. Oh, I will pose for him, you know. Stéphane, it's an honor. You're a worthy recipient of this medal. Am I already there? Okay. Well, that was quite a Surprise. Okay. Our second awards go to the Science Innovation Award, recognizing mid-career scientists. This year is named after Samuel Epstein, a geochemist who developed methods for reconstructing geological temperature record using stable isotope geochemistry. I'm delighted to present this award to Ariel Ambar from Arizona State University. Ariel describes himself as a scientist and educator interested in the Earth's past and future, and as inhabited world and the prospects for life beyond. And he and his teams have published on topics ranging from the origin of Earth's atmosphere to detecting life on other worlds and diagnosing human diseases. Ariel is especially recognized for his decisive contribution to understanding of biogeochemical processes in the ancient oceans and the atmosphere through non-traditional isotopes. Ariel met the lecture was this morning, and now, Ariel, in recognition of your innovative work, I wish to present you with the Samuel Epstein Medal. Congratulations. We have to look at the camera. Thank you. Now, our final award is the Harold Urey Award, recognizing outstanding contribution advancing geochemistry over an entire career. This year's awards goes to Erik Ölkers. Erik is recognized for his major contribution to the thermodynamics and kinetics of water-rock interactions. Furthermore, with experiments, he has characterized isotope fractionation during fluid-mineral interactions. He has quantified the weathering rates of the Earth's surface and the role of chemical weathering in the global carbon cycle. And finally, he is the leader of the development and application of carbon mineral storage in geoengineered systems. You will be able to hear Erik's meta lecture Wednesday at 8:30, again in room 111. Erik, in recognition of your remarkable achievements, I'm honored to present you with the 2019 Urey Medal. This is one. Yeah. Look at your camera. Done.
Thank you.
I now wish to invite Helen to introduce today's plenary speaker.
So thank you, Siggy. It gives me enormous pleasure to introduce our first plenary speaker this week, Bethany Ehlmann. Bethany is a professor at Caltech, and she also carries out research in the Jet Propulsion Laboratory. She's primarily interested in the chemistry of planetary surfaces, and indeed has done an awful lot of research on using rover technology, looking at Mars. And I believe this is what she's going to speak to us about today. So thank you very much, Bethany. I'm delighted.
Okay, thank you, everybody. It's a delight to be speaking with you this afternoon, and I'm going to share some of the latest and greatest findings from Mars. I will say, feel free to take pictures, because I hope some of the things in these slides pique your interest, because we need the engagement of the geochemical community to make sense of this incredibly rich data set. Because we are living in something of a golden age of Mars exploration. After you see the Mars exploration, all the reds on this plot indicate failures, crashed missions, missed the planet. But you can see that the 2000s and the 2010s have been remarkably successful. So we have a flotilla, and it's an international flotilla of orbiters, as well as landed assets on the surface, trying to unravel the history of Mars. Now, with the Apollo anniversary this past summer, I think it's really fitting to stop and think about what it is that makes Earth unique as a planet, what it is that makes terrestrial planets with atmospheres unique. Of course, one of the big questions is regarding, well, what are the conditions that make a planet like our Earth habitable? So what processes generate a habitable planet? Why do some planets sustain these habitats over billions of years, and others, perhaps Mars is an example of this, others do not, or others change profoundly in the course of their evolution. And then, of course, the big question, are we alone? Are other planets inhabited? So today we'll focus on the question of Mars, which I will show you that incontrovertibly was once clearly a lot warmer and wetter in the past than it was today. But the question is why, and then how did it change? Now, there's a rich record available to interrogate the history of Mars. What you can see here, and we'll start out our talk with a few slides on Mars at present. But what's important is that Mars records a period that we don't really have a complete record of even on our own Earth. The 50% of the rock record that is exposed at the surface of Mars, meaning you can drive up with a rover or send your lander there and immediately interrogate those rocks. 50% is from the first billion and a half years of planetary evolution, which on our own planet encompassed very important events, including the first water-lane sediments, the oldest fossil life, and the early evolution of our own atmosphere, as well as the interaction of our planet with a faint young sun that became progressively more luminous, and the effects of large impacts. Now, I said I'm going to start in the present, I'm going to go in the past. You'll notice that I'm going to give you kind of a tour of what we know about Mars, but the theme here is to follow the water, the carbon, the sulfur, and the chloride to try to figure out how these elements are cycling through time. So let's start at the present. Mars today hovers right at the edge of habitability. The day is not very different. It's nearly a 24-hour, 40-minute day. The axis is tilted right at the moment at 25 degrees. But of course, the distance away from the sun combined with the thin atmosphere that is less than 1% the thickness of Earth's combined to make the diurnal temperature range from a very cold 190 Kelvin at night up to actually temperatures above freezing during the day at the equator. Now, what I'm showing you here is frost, and frosts were very common for our Viking landers at the mid-latitudes. This is water ice frost in the morning. That's the white that you see in this image. For other landers at the mid to high latitudes, when they blow away the dust and the sand, beneath is water ice. Now, the closer to the equator, it's a drier, less icy environment. So this is a panorama that was taken by the Curiosity rover within Gale Crater, looking out from Mount Sharp. The sedimentary mound is causing to the crater walls. So it's a beautiful scene. But what we've learned chemically is that modern Mars is dominated by cold, dry, oxidative weathering. Perhaps, though, and this is the interesting part. This is where the frontier is in Mars science, though, perhaps with hints of even modern liquid water. Why do I say that? Well, one of the interesting things, and these are data from the Curiosity rover combined with analyses of the stability of perchlorate salts, specifically calcium and magnesium perchlorate. What you can see with the plot on the left is the temperature of the surface. What you see on the x as a function of the activity of water, and it's superimposed on the stability field of perchlorate. And what you can see is all those data points that are color-coded by time of the Mars year. What you can see is that for certain times of day, for certain seasons, you just nick the bottom end of that stability field where you could have the perchlorates deliquescing to form liquids, salt brine solutions. And it's predicted that this could be within the upper sort of 5 centimeters or so of the soil at certain times of years at certain locations. But we haven't actually observed this. We've tried. There's ChemCam, there's a laser, and we've looked to see if the soil has variable hydration state at night. So far, haven't observed it. But what we have observed is at a different rover landing site at Gusev crater, within the upper centimeters of the soil, what you're looking at here in the image is a place where the rover wheel scraped away the upper sands, and as it drug the wheel through the soil, what you see there exposed in the whites and the yellows are actually chlorine and sulfur salts. So, and what we see within these soils is actually a decoupling of chloride and sulfate. Collectively, when one looks at this data, one sees a profile, in fact, of chlorine, bromine, and sulfur as a function of depth in the regolith. And this points to the fact that there has been mobility of these salts to emplace them within this far from the surface over the time scale that these sands have been present at the surface of Mars. So this is interesting, this recent salt mobility. And what does recent mean? Probably means hundreds of thousands of years or less. The other exciting discovery on modern Mars, which could be a plenary talk in of itself, so I will leave this topic with only one tantalizing slide, is that certain of the spacecraft observing Mars have detected hints of methane. Why is this interesting? Well, Mars's atmosphere is mostly CO2, and it's also a highly oxidizing environment with UV radiation. So the existence of methane is fundamentally a disequilibrium that implies either recent creation or recent release of some ancient methane. Sources could be, well, the exciting one is biological. Sources could also be water rock reactions, volcanic emissions, or the release of very, very ancient methane trapped through other processes. So this is a hot topic area that's being continued to be monitored. Now, what could drive some of this activity? So I mentioned the very thin atmosphere, and in fact, it's quite thin. And so when we look at the phase diagram, there's only a small portion of Mars that for a small portion of the year, these contour lines are showing the small portions of Mars that for a matter of a few weeks has some amount of time in the course of a Martian day above the triple point of water. But what's really interesting and what we're starting to realize, the first sort of salvo in this came in 2011, is that the Mars we're looking at today is actually a little bit different than the Mars we would have seen even 100,000 years ago, because Mars does something that Earth does not do to the same degree. Mars has tremendous obliquity changes. So Earth, we know, is at 23 1/3 degrees. It maybe wobbles by a degree. And these types of Milankovitch cycles can generate ice ages. They've profoundly changed our climate on Earth. Now, Mars, which lacks a moon that its equatorial bulge can interact with to stabilize it, Mars actually goes through obliquity cycles of 10 degrees to 60 degrees. So it's wobbling on its axis, which changes the radiation balance and therefore where volatiles are stable on the planet. And it does so on these very fine timescales of just a few hundreds of thousands of years. Now, what we've seen and directly observed is that there's the same volume of atmosphere that we see in the atmosphere of Mars today is actually trapped in the polar cap of Mars. There's 5 millibars of CO2 that form in a vapor-solid exchange. How does this work? I don't have time to go through the details, but basically as obliquity, what I'm showing you here are the obliquity cycles. This is then the effect on atmospheric pressure. The dashed line is where we are today. And we can see for most of modern Mars, the last few million years, we've actually been at a much higher atmospheric pressure. But the CO2 comes and goes and comes and goes, occasionally with water ice layers off the southern polar cap of Mars in response to these obliquities. So while the Mars we're looking at today is at about 6 millibars, it's actually an equally common, if not more common, state that the atmospheric pressure is double, and therefore the more of the Martian surface for more of the year exceeds the triple point of water. So this is kind of interesting, and I think it's important as we're now going to step backward through Mars history. But something to keep in mind is that this variable present and the obliquity cycles and the effect that has on the atmospheric pressure as you go from solid CO2 ice to CO2 in the atmosphere, the present is really the key to the past here, and that the climate of Mars is not stable over timescales of more than a few hundreds of thousands of years. And this has been true throughout all of its history. So this is a bit of a contrast to Earth that we need to consider as we consider the evolution of Mars. Modern Mars hovers close to being habitable now, but we need to search for whether there's any evidence of groundwater, continue to monitor the methane to really understand whether there are modern habitats now, whether modern Mars could host life. These are some of the big questions, and we need to kind of follow up on the groundwater, follow on the methane to do this. We're going to spend the remainder of the talk now on that rich geologic record that I mentioned from the first about 1.5 billion years. And I'm going to focus in particular, because we have the most data on it, not on the third exciting question of was Mars inhabited, but we're going to focus on what the nature of the water-rich environments of ancient Mars were, and how that warmer scenario was possibly sustained. So this is an area where there's been a lot of change recently, because in 2003, the sum total of rock outcrops on Mars, where we had detected materials that were formed from liquid water, chemical evidence of liquid water, was basically 1, or 1 plus a few outliers. It was crystalline hematite in sedimentary units at Terra Meridiani, and we did land there, and I'll talk about that landing site. But thanks to the richness of orbital data from the European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter, we now know that there are thousands of outcrops across the surface with various kinds of clay minerals, silica, different kinds of salts, including chlorides, sulfates, and carbonates. And I'll zoom into a few of these dots on the map and show you what they represent shortly. Now, if we step back for a moment, though, and think about, okay, what is it we're trying to test here? We're trying to understand what were the environmental conditions of ancient Mars and use the geology and mineralogy as a tracer. And if we just consider 2 basic end-member scenarios for what happens to a volume of basaltic rock on Mars as it interacts with water, one is in an open system, sort of high water rock ratio scenario, similar to our own Earth with, in most parts of the world, with rain and integrated hydrologic systems. Eventually, over time, that basalt, what's left behind are iron oxides, aluminum clays. The more soluble ions, cations, are leached into solution, and then depending on the atmospheric gases, the magmatic gases, salts are precipitated elsewhere. In contrast, if you imagine a scenario where your rock is not being continually flushed through with water, either because you're in a closed system scenario or a low water rock ratio, you tend instead to end up with iron oxides, iron magnesium rich clays, and then fracture fills of other minerals. So we will now look at the evidence and see where different parts of Mars fall on this kind of end-member scenario for understanding the aqueous environments. And we're going to start with the first mineralogic evidence of water, and then we're going to move backward. So I already talked about the salty soils of the recent past, but then you have to go back about 3 billion years until you get evidence of liquid water on Mars that can be orbitally identified, so large enough that the signature can be seen from orbit. Of course, we know from some of the meteorites that there were small amounts of water interaction around 1.5, 2 billion years. Okay, so let's go back 3 billion years. And let's go to Nili Patera. This is a cone in a volcanic caldera, and one of the silica deposits that we see here are found in these small areas in and around the volcanic cone. So everywhere you see a dot here, it has this spectral signature, which has the SiOH combination and overtones of silica on basalt. You might say, oh, well, that's interesting. How much water was involved? Well, something that's interesting is that rather than kind of being uniformly distributed around the surface, as you might expect if there were simply a steam rock interaction, like a gas phase reaction. In fact, we see that the deposits follow slopes. So there seems to be a flow of liquid water involved here. The inference is that these are silica springs on the flanks of the volcano in Nili Patera. Now, we were able also to see silica deposits in situ. So this is a feature called home plate that was actually visited by the Spirit rover at Gusev Crater. This is what it looks like from the ground. You see these nodular, broken up outcrops here, partially covered by dust, but where you can drive up to them and stick a microscopic image, you see these bright nodular type textures. And measured for the alpha particle X-ray spectrometer, it's 98% silica. So these are almost like pure silica rocks in the highest places. Now, what are these? Well, there's a good argument to be made that these are, as we saw at the other site, the deposits that are formed by a combination of fumarolic activity in springs, such as Altatio, Chile. The morphologies are highly suggestive. The spectroscopy is as well, in terms of this is the stretch of SiO. We see a little shoulder here that's characteristic of sinter-type environments. And so what we're seeing here is, I think, fairly clear evidence of groundwaters percolating up out of the Mars surface that had leached silica from the surrounding basaltic rocks, possibly magmatic driven. Although interestingly, in this particular place, there are no sulfur or chlorine salts clearly associated that indicate a release of magmatic volatiles. But silica, 3 billion years ago on Mars in springs. If we go continue our march backward, now we start to get into a much richer period early in Mars history where water-rich aqueous environments were widespread, and the environments were segregated in time and in place. There's a diversity comparable to Earth, so we'll step through some of those examples. Now, if you were looking at this plot earlier, you should have noticed a few things. Well, first, I've grayed out the areas where ice and dust deposit at the high latitudes that kind of confound our analysis. But you might have noticed that the kind of bumpier terrains, those are older impact cratered terrains, are the ones that have the most hydrated mineral signatures. And in the sort of smooth areas and those around the large volcanoes, the recent lava flows 3 billion years and later, no evidence from orbit of hydrous minerals. But in the oldest terrains, they're abundant. Now, phyllosilicates, our clay minerals, are the most abundant, and I'll talk a little bit about those. They're mostly iron, magnesium, smectite clays. But what you might notice if you look at the salts is actually they're geographically quite distributed. And I'd say this is one of the big questions of why are these salts so segregated across the planet? So in the southern hemisphere, you've got these chlorides, but they don't appear to extend into the north. The sulfates are sort of patchy in and around Valles Marineris, which is the large canyon system to the next to the Tharsis volcanoes. And so you see the phyllosilicates are in the most region. The salts vary, and there's very little carbonate. We'll come back to that later. So let's step through these salt deposits on Mars and talk about what they mean. So let's start with the chlorides, and this is an area where there's ongoing work right now that I'll tell you about. So they were discovered back in 2008, 2010 timeframe was the very first global map of the chlorides. They occur mostly in ancient terrains, and they're often associated with clays. They tend to form, as you see in panel B here, within irregular shaped depressions. What does that look like up close? Well, here's a high-rise image that shows the scale of this image is about 2 kilometers across. That shows how the chlorides sort of interfinger between the topographic highs with clay minerals, forming these bright polygonally quasi-polygonal fractured deposits in between the clays. What is this? Well, I think an analog to the Martian chlorides is very much our Earth-type playa environments where chlorides represent one of the last phases to precipitate out of evaporating brines. Because they're the last phase to precipitate out of evaporating brines, chlorides then effectively can act as a date last experienced water, right? And so if we examine these chlorides and look and try to age date them, now I would love to bring a sample back and age date it the way we traditionally do in the laboratory. Can't do that. The best we can do is relative crater counts. And so the errors on these are hundreds of millions of years. But in the grand scheme of Mars, these are fairly young, these chlorides. In this case, the chlorides are superimposed on top of a volcanic flow from about 2.5 billion years. So that indicates that the last time that these chlorides were mobilized was actually relatively later in Mars history, around the same time as those silica deposits around the volcanoes. Something that we also see, which is very curious, and this is work by my student, ongoing work by my student, Ellen Liesk, is that they occur at a wide range of topographic elevations. Sorry, the x-axis got cut off. The x-axis here is elevation, and so this is a plot of approximately 4 kilometers of relief over this 2,000 some kilometer transect. So you can see that over this 4 kilometers of relief, the chlorides occur at multiple elevations, but interestingly, they don't occur in the deepest basins. Those are where sulfates occur, and the chlorides are restricted to these areas on the surface. And so the inference is that they're forming from small amounts of surface water at these multiple locations, while something else is going on in these deep basins. And so one of the things we're trying to figure out now in our welcome conversations is that this appears to be leaching of either dust or rock near the surface, but without a lot of other chemical weathering in the surroundings. Now, let's look at those sulfates. Well, we had the privilege of landing a rover at one of the locations with sulfates on Mars. That's the Opportunity landing site at Meridiani. And there, the story we were able to unravel in situ with close-up images taken by the rover. There, and some of you have probably seen this data before, these sedimentary rocks host, the matrix is primarily sulfate with about 20% amorphous silica, small amounts of other phases such as jarosite and hematite. Now, the hematite is both in the bulk as well as in these round concretions that you see that have grown within the sediments. The other things that you see in this image are crystal vugs left over from a prior phase, presumably a salt of some sort, that dissolved on the later stages of diagenesis. So this was a deposition of sedimentary rocks in water, followed by then multiple episodes of diagenesis, dissolving pre-existing crystals, forming hematite concretions. So that's the Meridiani sulfates. We see this story, we think, echoed elsewhere. Now, we've not been able to visit any of the other sulfate deposits on Mars, but models of groundwater upwelling predict that in some of the deepest basins in the floors of the Valles Marineris Canyon system, that this is going to be an area of upwelling groundwater from the surroundings. And indeed, there are kilometer-thick deposits of polyhydrated sulfates and monohydrated magnesium sulfates like kieserite that we can detect via orbit and then localize in these layered deposits. We're able to look at a few locations in great detail, and the remainder of these slides that I'll show are from the area called Terra Serenum, which is an area of predicted groundwater upwelling, where you can see that these impact craters are sites where it was predicted that there's groundwater upwelling, as well as then the potential for evaporation. Now, what we saw when we looked at this one crater, Cross Crater, which is a 70-kilometer crater, is that there's a kind of dark, flat floor in the center. But in the sedimentary rocks that are exposed around the perimeter, there's a mineral assemblage that includes alunite, kaolinite, and so we have an aluminum phyllosilicate signatures associated with aluminum sulfate hydroxides, the alunites. And this is an indicator that, number one, there's been an extensive amount of leaching if the starting materials were basalt. And number two, that there's an introduction of sulfur into the system and a creation of acidity to form the alunite. So the hypothesis at this point was that, well, what's the way to do this? Well, perhaps we're having the fluids that are the groundwaters that are coming into this lake interacting with a magmatic system similar to the propylitic type of alteration that you see with kaolinite and alunite deposits on Earth, where disproportionation reactions generate acidity from the sulfurous gases that are coming out of these systems. We didn't really have any particular proof of this beyond circumstantial evidence that, well, maybe it was a few hundreds of kilometers from the nearest volcano, which it was, until more recently, looking into another crater and following up on these light-toned sediments. What we found when looking in this 40-kilometer crater was actually volcanic features in the floor of this crater that has a ring of kaolinite and alunite around it as well. So in some of these sulfate basins, there's clearly a linkage to volcanic activity, but it's a little bit confusing. We have these huge groundwater-formed large sulfate deposits on Mars, heterogeneous mineralogy depending where you are in the planet, either iron oxide jarosite at Meridiani or alunite and aluminum phyllosilicates elsewhere. And so there's sometimes the source of sulfur seems to be magmatic, but this is a bit of a mystery, a mass balance mystery as to where these large sulfate deposits on Mars came from. Continuing to march through, not all lake basins are full of salts. So there are hundreds of open enclosed basin lakes across Mars. We have been able to land at one that was very deep, and that's Gale Crater. So Gale Crater is a 150-kilometer diameter crater, 5-kilometer hole in the ground, that even before orbit, we inferred would have once hosted a central lake. Now, as seen from orbit, Gale was also incredibly intriguing because in a layered stack of eroded sediments in the center of the mound, there was a progression between units that had a mixture of hematite and silica, then stepping through to a hematite-enriched ridge, phyllosilicates, sulfates. So a very clear progression through time of changing water-rich conditions. So that's a great place to go to look to unravel the history of Mars. So I'm going to be talking about some of the initial work from this detailed study of the rock record at Gale Crater through to some more recent findings. Now, what's fortunate about having a rover on the ground is that you have an amazing, especially in the case of the Curiosity rover, you have an amazing analytical laboratory. We carry SAM, the Sample Analysis at Mars Suite, which is a mass spectrometer, tunable laser spectrometer. There's an XRD in the belly of the rover. So in addition to our remote sensing instruments that include multispectral imager MASTCAM, LIBS instrument called ChemCam, and then the APXSX spectrometer and microscopic imager on the arm. In addition to these geologic instruments, we also have this analytical laboratory and the ability to drill a sample on the surface and then ingest it into the rover for analyses. So we were very fortunate that when we first landed, one of the first things we saw was really what had drawn us to Gale in the first place, which was clay-bearing mudstones, in this case with little small diagenetic nodules, probably of clay, as well as these white veins of calcium sulfates. Now, what does that look like chemically? Well, it actually looks chemically kind of like basalt, even if mineralogically, from the XRD, it was about 25% or so smectite clay. The alteration we found here in Gale Crater Lake was mostly isochemical. And so if we leave out silica for the moment and plot on this ternary diagram with the alkalines and alkali earths, aluminum and iron magnesium, all of those sedimentary rocks plotted here, which is similar to the field of basalt. When basalt weathers, it usually migrates up along here to form montmorillonite and iron oxides. But we weren't seeing that at Gale. Instead, all of the data were clustering. These are the data now from ChemCam, which allow us with the LIBS to take hundreds of micron spots on the surface. What we see here is that same cluster of points, and then with ChemCam, we were able to target uniquely some of those little veins, so heading out to calcium sulfate here. Now, what was interesting, though, is, and to think about, is sort of, well, the implications for this water-rock reaction, and I'll wrap back to this at the end of the talk. One of the things that we saw is lots of early diagenetic features. Here you see these ridges within the sediments, and a lot of hard work by Katie Stackett and Kirsten Seebach showed that these were early diagenetic. But what's important actually here also is what's happening chemically, and this is some work by Tom Bristow and Nick Tosca. So to explain the chemistry that we see from the XRD, which was dominantly about 20 to 25% smectite clays of various sorts, as well as amorphous phases, a diminished amount of olivine relative to the sands, and an abundance of magnetite. What's proposed is the reaction that was taking place in situ here within Gale Lake, in the lake bottom sediments, was a reaction involving water, aqueous silica, and aluminum and magnesium iron sulfates from the basaltic materials, leading to reactions to form magnetite or smectite clays of various sorts, as well as the Tom Bristow notes. These reactions require additional balancing via the addition of oxidants as reactants or the production of hydrogen gas. And Nick Tosca took this a step further to model exactly what amount of hydrogen gas could be produced, and could this be responsible for those nodular features and these vein-like features? And we think that the answer is yes, that you get a significant amount of hydrogen gas being produced from these water rock reactions in the subsurface of Gale Lake. Okay, we didn't just see modeled diagenetic sediments of the lake. We saw some spectacular millimeter and centimeter scale laminae from the fluctuating lake waters. But what we also saw again and again is the evidence of this overprinting diagenesis. So you can see here large veins coming up into some of the outcrops. We can take a closer look, as Rachel Kroniak has, and see here that there are actually multiple generations of diagenesis, groundwater-driven fracturing and mineralization, including some of these black, very dark veins, these much lighter tone veins. In fact, if you zoom in over on the side here and take some microscopic images, you can really piece together a story where you have the sediment deposition in a lake, then you have a second episode of water flowing through that forms these dark gray magnesium-rich veins, a third generation of water-related activity to inject these calcium sulfate veins, and then even cross-cutting those calcium sulfate veins, another generation of dark tone veins. In this case, we were able to pinpoint with LIBS. We don't really know what the mineral phases are, but that these are more iron and potassium and even fluorine enriched veins coming into this system. So hot off the presses, we don't fully understand it, but what are the drivers of diversity, the drivers of this episodicity and the changing chemistries of water in Gale? Also on the diagenetic side was the exciting result. When you have a mass spectrometer on Mars, you can even do age dating on planetary surfaces, and I think this is an exciting new capability for the coming decades. But here with potassium-argon dating, using those ingested samples, measuring the composition of the jarosite, the age that's obtained is on the order of 2 billion years, which, if true, implies that that was when waters were last going through these sediments. Now, so the story of alkaline lakes, groundwater-related diagenesis has continued as we've gone up Mount Sharp, but there have also been some changes as we've continued to traverse through this mineral stratigraphy, and I'll show kind of quickly here some of the results that are coming in. So this is the work from the Chemin XRD team that shows what the plot over here shows a decreasing amount of pyroxene, so decreasing igneous minerals as we go through this sedimentary sequence, somewhat variable, but perhaps increasing calcium sulfates. Again, changes in clay mineralogy, and then a transition from these magnetite to primarily almost exclusively hematite and more oxidized iron-rich minerals as we've gone higher. The other thing that we've seen is a much greater abundance of salt, including bedrock units with up to 30 to 50 weight% of sulfate in them. And so this is all of the initial work that I showed you from Gale Crater was from the bottom part of the stratigraphy here. Something interesting happened as we got to the Sutton Island member. We started to see much more calcium sulfate as well as other salts. So these calcium sulfates, we started to see bedrock exposures with up to 30 to 50 weight% calcium sulfate, trending on the line to gypsum anhydrite or basanite. The other thing that we saw in this vicinity was abundant mud cracks, such as preserved in these sedimentary rocks here. And finally, and interestingly, these purple dots here indicate our areas enriched in magnesium. And in fact, they're enriched in magnesium and sulfur and hydrogen. And so what we think we're seeing is a mixing line between typical bedrock and then the addition of magnesium sulfates. And that's interesting because magnesium sulfates are highly soluble and they're a late stage precipitate from briny waters. The final thing that we're seeing here, if we put chlorine on a plot, chlorine has been variable throughout the traverse, but we start to see some high chlorine areas where chlorine and sodium are correlated. So what's happening here? Well, I think we're starting to see some briny waters in Lake Gale. So what we would predict is if our waters are evaporating, we should precipitate out gypsum, but then magnesium sulfate and sodium chloride will not come until the later stages of evaporation. And so what I think we're seeing is the chemical signatures of a retreating lake level leaving behind isolated pools where the brines can evolve to a high degree of salinity. And we'll see what the rover has to come, because the rover has kept going, and there are more units to come, and you'll hear some of those talks this afternoon. Okay, I think I've got about 10 minutes left. Is that right? Can someone nod or something? Maybe? Maybe? Yes? Okay. So now we're going to go, we haven't gone yet, to the very oldest, deepest parts of the Martian stratigraphy. What does the oldest part of Mars look like? Well, we'll zoom in here to the area around the Isidis Basin, where fortuitously, a combination of tectonic fracturing and then subsequent erosion have exposed a deep into the stratigraphy of Mars. The age of the units that we're looking at is set by crater counting of the Isidis Basin itself, which is about 4 billion years old, and then bracketed by crater counts on these Syrtis Major lavas that come up on top, and those are about 3.5 billion years old. So sandwiched in between is a pretty amazing preserved stratigraphy. The lowermost units exposed in mesas in and around the troughs have caps of unaltered low calcium pyroxene, but beneath up to 600 meters of iron magnesium smectite-rich sediments. My title slide was actually from this area, because when you look at those iron magnesium smectite-bearing sediments up close, you see they have these amazing ridge systems that we infer to be fractures that were mineralized by waters flowing through, perhaps relatively soon after these formed following the impact. Now, above them, though, are these bright-toned, banded materials stratigraphically above. We can get a little bit better look at what's going on if we go elsewhere. So I'm giving you now a false color image that maps the colors to the mineralogy that we're observing from orbit. And if we zoom into that same stratigraphy, but now we have the ability to color code it with our infrared imaging spectrometer from orbit, what we can see is that the ridged materials here are in the lower portions of the stratigraphy, these iron magnesium smectite-bearing materials, capped by then, in the yellow-greens, magnesium carbonate-bearing units in green, olivine, and yellow. Now, if we zoom in, what are these white dots, anyway, within the iron magnesium smectites? Well, they're some of the oldest materials that we have on Mars exposed at the surface. They're giant breccia blocks, tens of meters in size, that were excavated by this Isidis impact. And they also hold a very ancient record of conditions on Mars and have variably unaltered, at least from orbit, low calcium pyroxene bearing materials, as well as iron magnesium smectites. And some of these appeared to be layered, either sedimentary layers or volcanic layers. Now, if we go back here and we look at the olivine carbonate rocks, the next rocks stratigraphically above, we can see that they're fractured on sort of few meters scale. So kind of banded, fractured. What's going on? Well, the answer is we don't know, so I'm still happy to take your ideas, but the best analog that many of us have been able to settle on is perhaps what we're seeing in these olivine-enriched rocks is something similar to what you see if you walk around on the Oman ophiolite, where you have ultramafic rocks that were either altered on the seafloor but are still altering today at the surface through weathering and alteration and then ongoing serpentinization at depth, where you have veins of magnesium carbonate precipitating in between the fractures with ongoing serpentinization at depth. And this is an example of what it looks like. So you might ask, well, do you see serpentine associated with these? The answer is sometimes. Serpentine is relatively rare on Mars, but it is associated with these olivine carbonate rocks and nili fossae. It's also associated with just sort of jumbled, very ancient rocks where the mineral signatures do not, in this case, follow any obvious stratigraphy, that we see signatures of serpentine, chlorite, a phase like an illite or a muscovite, and kaolinite, all in very close proximity, but in a sort of jumbled assemblage. These, in fact, are seen in some of the oldest materials exposed around the Tharsis volcanoes and Valles Marineris. In fact, these are one of the few evidence of sort of large-scale tectonic deformation on Mars. Well, these are the areas with serpentine, and so what that exactly means, we do not yet know. But if we look at the oldest, deepest units of Mars, what we primarily see are iron magnesium phyllosilicates, these smectites, chlorites, serpentines, found mostly exposed in thousands of impact craters, but in a few places erosion has been our friend and we can access them more readily. So I'll, I think, leave here with what's going to happen next. So Mars 2020 is going to land in another deep lake basin, Jezero Crater, but it's going to be able to exit the crater and traverse through the stratigraphy that I just showed you here. So the landing site actually is within this impact crater, and it's in a watershed that cuts through all those units of carbonate and clay that I just showed you to form this spectacular delta. So this will be the landing site of the 2020 rover, which is a sample collection rover, and the rover will land on the floor, traverse up the delta, collect samples, what lies ahead in the delta. It's pretty spectacular. There are layered sediments and then evidence of rocks that preserve the stratigraphy from above. So our environments are changing through time. Is this mineralogy exactly what we would have expected a priori if we took what we know from Earth and translated it to Mars? I unfortunately don't have time to go through the details here, but maybe I'll leave you with this thought experiment and then zip to the conclusions of it. So when we look across this setting, if this were Earth, what we would actually see are sort of aluminum phyllosilicates, iron oxides, lots of carbonate, and then occasionally other salts. And our carbon cycle on Earth, of course, we know well. It has these components, tremendous change. On Mars, though, you have to cross out, of course, the whole entire biological side of the carbon cycle, or at least we think that was not important, as well as probably cross out the subduction side. And so this is something that people are grappling with now. Are there geochemical cycles on Mars, or are the cycles mostly one-way? That is, one-way loss out in the space, or one-way loss to the crust. So something that we're looking at right now is and I'll refer you just to the paper by Renyu Hu, is that we are living in an amazing time where we have orbital data on atmospheric loss rates. We have isotopic measurements of the atmosphere and in some cases of stable isotopes in the rocks from MSL. We have knowledge from meteorites of the mantle composition, and we're starting to get knowledge of the quantities of salts selected. So we can start to build our actual chemical models constrained by isotopes for the first time and model the amount of actual carbon deposition. And it's looking like, in terms of CO2 in the atmosphere, that it was always relatively thin, no 5-bar atmospheres or something to promote greenhouse warming. So I'm going to suggest, and I'll leave you just with this thought, that one of the things we need to consider are some of the things I mentioned earlier. So there was a period where there was water on Mars, but with those obliquity cycles changing, that would have come, that would have gone, but has been ample evidence of groundwater over and over again at each of the sites I showed you. So do we need to think about a different cycle for Mars climate and making Mars warm and wet? Perhaps one where we have igneous minerals being altered through weathering or hydrothermal activity to create reduced gases. With my colleague Robin Wordsworth at Harvard, we've been modeling the effect of these reduced gases on the atmosphere, and you can get substantial warming. Not enough to make Mars warm and wet, but warmer and wetter such that you get liquid water for sustained periods of time. So this is kind of the frontier, is really understanding the geochemistry of these water-rock reactions and what they can hold for the future. And so I'll leave it here with some of the key investigations for the future. I think we need to do petrology at multiple sites. We need rovers like MSL and the MERS that can look at these mineral signatures that we see from orbit and really decipher what they mean environmentally and what they mean in the time ordering. Ideally, these would have the capability of doing isotopic measurements in situ, because that just adds another lever on your ability to actually quantitatively constrain these geochemical cycles. So between multiple rovers at multiple sites, and there are 2 upcoming from the European Space Agency and NASA, coupled with sample return, I think we have a great ability to access this early period in the history of terrestrial planets and really decipher some of these early processes that were going on, the nature of the geochemical cycles, and really understand what sustained Mars's early habitable environments, why they changed, and then figure out if any of those environments were once inhabited. So thank you. I'll leave it there, and if we have time, take any questions.
So thank you very much, Bethany, for a fascinating talk. So yep, it'd be great to have some questions. There are microphones in the aisles if people want to use those. Do we have any questions?
Everyone's hungry for lunch.
Well, absolutely.
Oh, there is one question.
Is there
I see
one
one question, yeah. Yes, yes.
So my question is, how do you see this transition from more alkaline condition to acidic condition on Mars?
Yeah, so the question is, and I didn't really talk about this, how do you see the transition from alkaline to more acidic conditions on Mars? So classically, there's been this view, which is largely correct, but classically there's been this view that early in the history, with the iron magnesium smectites, the chlorites, the serpentines, the carbonates, there were more alkaline environments, and then as we get later in history, we have sulfates, chlorides, etc., jarosite, more acidic. I think the answer is twofold. I think maybe the transition wasn't necessarily as sharp as it perhaps first appeared, because I think even if we go back in time, there will still be a diversity of environments, some of which are acidic when we have contribution from magmatic volatiles, for example, and some of which are alkaline. That being said, there is a broad trajectory in Mars history that when you go later, you enter more water-limited conditions. So maybe that's part of the puzzle, is that as you get into more water-limited conditions, the interaction of the water may primarily be with magmatic type volatiles, sulfur and chlorine coming out of volcanic systems in groundwaters in local locations, or with volatiles that are precipitated on the surface in dust. That may be one explanation.
That's great. Do we have any more questions?
Yeah, one more. And then people can... Where's the water now, is the question. Yeah, in fact, that is the paper that I'm going to be working on while sitting here at this conference. So one of the questions is, what has happened to the Martian water? I think what's happened is twofold. One, some of it's escaped into space, and the MAVEN mission, hydrogen escape. And the MAVEN mission has quantified the rates of that, and it's something equivalent to, like, if you were to take 25, 30 meters of water and cover the planet with it, that amount has escaped into space. And then you might say, if the hydrogen has escaped, what's happened to the oxygen? Well, some of the oxygen has escaped to space, and some of it has gone into oxidizing the basaltic materials to form iron oxides. Now, that being said, if you add up all of the morphological features with liquid water, big outflow channels, valley networks, etc., you actually get a lot more than a couple few tens of meters. And so the question is, where are the rest of the water? I happen to think a substantial amount of it has been sequestered in the crust, and volume calculations are underway. But we have no subduction cycle on Mars to recycle it, right? So it's a very different system. Once you end up in the crust, you might be done for in terms of water.
Well, thank you very much. That is a
All right. Thank you, everyone.
tantalizing note to
Happy
leave
to
things
talk
on.
more.